Hi everyone, so we'll go over this problem here where we're dealing with an elevator. So we're told that the figure here shows the velocity versus time graph of a 75 kilogram passenger in an elevator. Oops, sorry. So we know the mass of our person is 75 kilograms. We are told then to find the passenger's apparent weight at the time of 1 second, 5 seconds, and at 9 seconds. Right, so remember, whenever it's asking for apparent weight, right, it's not the actual weight. Right? Actual weight is just the force of gravity that's equal to mg. Apparent weight is essentially telling us what the what a scale would read if they're sitting on some sort of a bathroom scale. This is essentially the normal force. Right, so we need to find the normal force acting on this person at these various times. Right? Because we're given a velocity versus time graph, this gives us the information to find acceleration. Right? So we basically have three chunks, so to speak, of acceleration. We've got a constant positive acceleration here from 0 to 2 seconds, right? And we can find that acceleration by taking the slope of this graph. Because we know that acceleration, or average acceleration, is going to be your change in velocity over change in time, right? And the average of a constant acceleration value is just the acceleration, right? So here our acceleration is going to be 8 meters per second divided by 2 seconds, right? And that gives us a value of positive 2 meters per second squared, right? So I'll just kind of make a little table here for our time and what the acceleration is. So the time from 0 to 2 seconds, our acceleration we found to be a positive 4 meters per second squared. Is that what I said before? I don't even remember. Right. So it's just we're doing basically we're calculating the slope. So for 2 seconds we have a change in slope of 8 meters per second, change in height of 8 meters per second. All right. So next chunk is this middle chunk here from the time of 2 to 6 seconds. Right there. Our slope is 0. We do not accelerate. We stay at that constant velocity. So acceleration is 0 there. And then finally, from the time of 6 to 10 seconds, so that's a time of 4 seconds, we go from 8 meters per second to 0 meters per second. So our change in velocity is now negative. And we go from, let's see, a height of negative 8 over 4 seconds gives us negative 2 meters per second squared. Right. So now we have found our acceleration values for the corresponding time. Right. So looking at, let's say, time equals 1 second, right, if we draw a quick free body diagram, right, we know we have the force of gravity straight down. That's just going to be the mass times acceleration due to gravity. Right. And we know we have a positive acceleration, so I'm going to call upwards as positive. So we know our normal force that's acting straight up is longer. It doesn't look very much longer, does it? Let's draw a little bit more exaggerated. All right, so our normal force we know has to be bigger since our net force has to be in our positive direction in order for acceleration to be positive. So our normal force here is what we're solving for. We're solving for apparent weight. So if we were to sum our forces in that direction, right, we have a positive normal force and a negative weight, right? And we know the sum of the forces, that's equal to mass times acceleration. So our normal force here is going to be equal to our mass times our acceleration plus the acceleration due to gravity. Our mass is 75 kilograms, and our acceleration is a positive 4 meters per second squared plus our 10 meters per second squared. So essentially our normal force, our apparent weight, is going to be 75 kilograms multiplied by 14 meters per second squared. Which, if I grab my calculator, sorry for this away, 75 times 14 gives us 1,050 newtons. That is our apparent weight at the time equals 1 second. Right, now we look at the 5 second mark. Well, at the 5-second mark, we do not have any acceleration, so at 5 seconds, our normal force is equal to our weight. All right, so essentially our sum of the forces here is now 0. All right, so our parent weight is equal to mg, which is just going to be our 75 kilograms times our 10 meters per second squared, gives us 750 newtons. And then finally, we have the region, so at 9 seconds, that's in the region where we're accelerating negatively at negative 2 meters per second squared. So if I draw my free body diagram for that situation, now my weight, mg, has to be larger than my normal force, because we're accelerating downwards. So now if I sum my forces, all right, we have, again, still a positive normal force and a negative weight is equal to mass times acceleration. So same formula as before, but now our acceleration is negative, right? So again, here I'm calling upwards positive still, so my acceleration is negative. Generally speaking, I don't like calling my direction being positive, not the direction of acceleration, but we're going to go with this problem. So I still end up having the same formula as above, right? But this time my acceleration is negative, so we take our 75 kilograms and we multiply it by negative 2 meters per second squared plus our 10 meters per second squared. Wow, almost off screen there. Really hard to read, right? But that sums to be 8 meters per second squared, right? So we have 75 kilograms times 8 meters per second squared. 75 times 8 is 600 newtons. So that is our parent weight. I hope that was helpful.